complex numbers. Now, this is the kind of our last objective to talk about the roots of complex numbers. I wanted to recall something from the fundamental theorem of algebra. So the roots of complex numbers. I want to talk a little bit about some algebra, things that you may have forgotten, or may have not been taught, depending on how drunk your teacher was. No, we're kidding. Okay, now, if I have this equation, x to the 6 minus 1 is equal to 0, for example, the exponent, or the little number on the top here, tells me how many answers there are in this equation. So the 6, or the degree, that's a fancy word. So the degree tells me how many answers there are. Alright, so in this case, there's six degree, so there's 6 answers. So there's 6 answers to this equation. That is to say, there are 6 numbers. This means there are 6 numbers when taken to the 6th power. Wow, that looks horrible. There are 6 numbers when taken to the 6th power that would equal 1 for this example here. Alright, 6 numbers taken to the 6th power will get me 1. That's what this equation tells me. And we learned that from the Nth theorem of algebra. And of course, if I sat and I did the ugly factoring involved in this equation, it would look something like this. It would look some ugliness like this. X to the 6 minus 1 equals 0. This is difference of squares. This is x cubed squared minus 1 equals 0, which ends up being x cubed plus 1, x cubed minus 1. And after all this ugliness, this is it's a sum and difference of cubes, so it involves even uglier formulas of x plus 1 times x squared minus x plus 1, and then it ends up being x minus 1 times the other ugly formula, x squared plus x plus 1. All equals nothing, and you would sit here and do painful algebra, and you'd start crying. And well, for this one's not that bad. So then you would set all these hideous ugly numbers to 0, plus 1 is equal to 0, x squared minus x plus 1 equals nothing, x minus 1 equals nothing, x squared plus x plus 1 equals nothing. On these two, you use quadratic formula. On those two, it's just x equals 1. Your textbook on page 454 has the answer to this equation, but I don't feel like doing all that. Let's face it, that's a lot of work. There's actually an easier way to do that, and that involves the nth roots of complex numbers. So that's what we'll be talking about in this video here. The first thing I want to look at is we need to define what a root is. So let's define it. Okay. So definition. The nth root of complex number. The complex number u equals a plus bi is an nth root of the cube if z is equal to u to the n is equal to a plus bi to the nth power. That's ugly, and it looks kind of fancy. But this is the formal definition. Let's translate that into English. If I can take that number and raise it to whatever power, then it is an nth root. Then it is an nth root. Okay. So that's what this means. But in order for us to work with that, we need a hideous, ugly equation. So let's start by talking it out. Let's start by getting a formula. Let's do that the ugly, fancy way by using a new piece of paper. So we need to start by defining what u is. We're going to rewrite u in trigonometric form. Okay, so we're going to let u equal s cosine of n. Oops, sorry. We'll let u equal s cosine of beta cos sine of beta. Now, you may ask, why did I use s and beta? These letters are arbitrary and I can really make them up. But since we use s, since z is used with r and theta respectively, we'll use different letters for that. Okay. And we'll let z is equal to r cosine theta plus I sine of theta. Everybody agree with me so far? Well, I'm defining what I'm working with. So now that I've defined what I can work with, you know that if I use Demoivre's theorem, that z is equal to u to the n. And we're going to cheat and use Demoivre's theorem for this. Okay? So u to the nth power is this hideous, ugly thing to the nth power. So let's plug it in. So we plug in the ugly thing, s cosine of beta plus I sine of beta to the nth power. And using Demoivre's theorem, I know that the n will, of course, moduli gets raised to the power of n. So s to the n, and then the angles get multiplied by whatever power. N beta sine of n beta, like that. Okay? Now, because this is an equation, I can equate it mathematically. This will equal r, it's not r to the n, just r, of cosine of theta with I sine of theta, like that. Okay. Everybody follow, because z is equal to u to the n. Now, it's relatively obvious if I'm equating pieces of the puzzle, I can equate it like this. I can equate, because it's an equation, I could state that s to the n is equal to r cosine n of beta is equal to cosine of theta, and of course sine of n beta is equal to sine of theta. Right? Just using the equation by pieces, equating pieces. The other way is to cheat and take the absolute value of the whole thing, which it's technically what you're doing anyway. Okay? Now, if I know that r is equal to s to the n, I can just divide and get rid of r. R is not really relevant to the discussion. So from here, it's just a matter of recognizing what I have to work with. Right? I know that n beta must equal theta. So from here, let's go to the next page. N beta equals theta. And the angle, remember that in any trigonometric equation, especially with sine and cosine, the angles differ by their period. And the period of cosine is 2 pi. So we'll use this special number here, 2 pi k. So n beta is equal to 2 pi k. This is a very important expression here, because what I'm stating is that the angles, all solutions to this problem, differ by a certain amount of angles. And we're working in radians, if you cannot tell, because radians is a lot easier to play with. So if I divide both sides by n, I can obviously get an expression of beta is equal to theta plus 2 pi k divided by n. And I can substitute that back into the equation, and this is where I get the equation that is on page 455. So where I get that equation from. Okay, I get this beta is equal to 2 pi. And then from here, the other equation I have, s is equal to r to the nth power, correct? Or sorry, not s. Sorry, I wrote it wrong. S to the n is equal to r. If I take nth root of both sides, I get r to the n. I get s is equal to r to the nth power, or the square root of n, nth root of r. That's probably really. Okay. So we get s is equal to the nth root of r, like that. Now, I use back my equation, which is u, when I rewrite that on the next page, which we know that u is equal to s cosine of beta plus I sine of beta. From here, I know that s from the previous page is equal to square root of nth root of r. So we have the nth root of r cosine of beta, which is theta plus 2 pi k divided by n plus I sine of theta plus 2 pi k divided by n. That whole expression there. And this is the nth root of a complex number equation. Kind of ugly piece of junk. Okay? And so on this page it says to define the nth root. And I'm going to define what k is. K is on numbers 0, 1, 2, 3, n minus 1. Why is that? because it's in a circle. Cosine and sine form, of course, as you know, circular functions, and in a circle, these numbers repeat. So what ends up happening, let me draw a picture for you, is that you get this big giant circle, and along this circle are all the answers to your equations. And if you have, let's say for example, here 4 roots, can't draw, but you'll have to deal with it. This is 1, 2, 3, and 4. If there's 4 roots, there's 4 roots, that means n is equal to 4. What ends up happening if we go 0, we go 1, 2, 3, 4, it ends up repeating. So actually this should be 0, 1, 2, and 3. So if we go 0, 1, 2, 3, if I go to 4, I end up back at the place I started. So that's why we only go to n minus 1. Okay. And it's interesting to me that we end up with this kind of circle. The circle is sometimes called, that forms the nth roots of unity. Sometimes that's what this circle is called, the nth roots of unity. And their union is that, the unity is that all the numbers here form whatever number you took the nth root of. So if you're trying to get, for example, like we did earlier, this problem on this page, here, the 6th root problem, if there are 6 answers, all 6 of those answers will be on that circle. Okay. So let's do an example of how to do that. Let's find the 6 roots. Something like this. 6 squared minus 1/2 is equal to 0. Ugly. Ugly problem, which you could probably do using quadratic formula. Who the F wants to do that? Actually, let's just not use 1/2. That's going to end up being ugly. So let's use the 6 roots. We'll do x to the 6 plus 1 is equal to 0. Okay. Okay. So now to solve this problem, the first thing we're going to need to do is, of course, move the 1 over. So if we end up moving the 1, so isolate the variable. So this ends up being, of course, x to the 6 is equal to -1. At this point, your algebra geniuses, you should be able to move that over without a problem. So then I need to rewrite 1 in terms of a trigonometric form. Rewrite 1 in its trig form, and since it's -1, it's going to be on an angle on the quadrant. It's called a quadrantal angle. And since it's -1, it'll be on the x-axis. -1 will be on the x-axis, and cosine of pi is -1. So we'll rewrite this as x to the 6th is equal to 1. And so now, you may ask, why did I try +1 instead of -1? Because the -1 will be taken care of in the cosine of pi. Cosine of pi plus I sine of pi. Like that. So we rewrite it in trig form. So I remember that cosine of pi is equal to -1. So that's where the -1 goes. It goes away. Now, from here, I need to use the equation for here I need to use the equation for the nth roots. So we're going to use in part C. So part C we use the nth root equation. So we go nth root of r cosine theta plus 2 pi k divided by n plus I sine of theta plus 2 pi k divided by n. We are, of course, finding the 6th root of this equation. So this will be the 6th root of 1. So it will be the 6th root of 1. And cosine of pi plus 2 pi k and it's divided by 6 because we're finding the 6th root. And of course pi plus 2 pi k divided by 6. And so from here we plug in our different numbers, which are 0, 1, 2, 3, 4, 5 respectively. So we know k equals 0, 1, 2, 3, 4, 5. So plugging in 0, 0 times 2 pi is nothing, so everything goes away. So it's just going to be pi over 6. So in the first one, we have 6 root of 1 cosine of pi divided by 6 plus I sine of pi divided by 6 and 0. Then for 1, by the way, the 6th root of 1 is just 1, so you can have ignored it. But I'm writing it for the sake of showing you an example when you're going to want to have that there. So in the second situation, we have pi, k is 1. 1 times 2 pi is 2 pi. 2 pi plus pi is 3 pi. 3 pi divided by 6 is pi over 2. So this ends up being cosine of pi divided by 2 plus I sine of pi divided by 2, which of course simplifies to I. But again, you can just leave it in the trigonometric form. The 6 square root of 1 cosine 2 pi times 2 is 4 pi. 4 pi plus pi is 5 pi, so it's 5 pi over 6. Sine of 5 pi over 6. I'm not having you convert it back into standard form because I want you to just know what the regular forms here are. Again, 6 root of 1. Cosine. 3 is 6. 6 plus 1 is 7. Of course, 4 times 2 is 8. 8 plus 1 is 9. So it's 9 pi over 6. But of course, 9 pi over 6 simplifies to 3 pi over 2. Which this simplifies to negative I. But who's counting? Okay. And then the fifth root, finally, 6 root of 1. And the sine 5 times 2 is 10. 10 plus 1 is 11. Pi divided by 6. I sine 11 pi divided by 6. So these are the 6 roots that belong to the circle. And they form a nice pretty circle. I'm not going to draw that for you because I'm not an artist. So that's the idea. So they form a nice pretty circle, and all of these numbers taken to the 6th power will be -1. Isn't it lovely? So all of these numbers, 1, 2, 3, 4, 5, 6, 6 of them solve the equation, which will be -1. If I take all of those numbers and raise them to 6th power, I will get 1. Okay? Everybody got it. And I'm not going to do any with degrees because we're just converting them all to radians anyway. So, next time we'll talk. Not sure yet. But we'll do some proof. Maybe I'll do the proof for Demoivre's theorem by induction or something. We'll see. Anyways, good luck. Okay.